Welcome to Summarize Science. Today, we're looking at a paper titled Integration of Porous Graphene and 3D Printed Piezopolymer for Flexible Ultrasound Transducers. Simply put, it's about making flexible, wearable ultrasound patches that can see inside your body. We all know ultrasound is incredibly useful in medicine, but the ones used by doctors are rigid and sometimes bulky. This makes them less than ideal for applications where you might want continuous monitoring or imaging on a moving, contoured part of the body. To solve this, researchers have developed an innovative new way to create these devices. Their approach combines zapping a plastic film with a laser to create graphene, and then 3D, printing a special sound-generating polymer directly on top. This process is fast, scalable, and remarkably cheap, with a material cost of less than $5 per device. Here you can see the concept, with a photo of the final flexible patch comfortably sitting on a forearm. The key innovation is using what's called laser-induced graphene, which has a porous, sponge-like structure. This porous texture allows the 3D printed polymer to embed itself into the graphene electrode. This creates a much better connection between the parts, which is crucial for performance. This diagram shows the simple 6-step fabrication process. It starts with a standard plastic sheet, which gets zapped by a CO2 laser to form the patterned graphene electrode. After printing interconnects, they 3D print the special piezopolymer, which is the part that converts electricity to sound and back again. So, how much better is this new design? To find out, the researchers created a control device using a traditional flat silver electrode and compared it to their porous graphene version. The results were significant, with the graphene-based transducer producing a signal amplitude more than 3 times stronger than the silver-based one. Of course, a strong signal is useless if it can't create an actual image. So, they put the patch to the test by imaging several targets in a water tank. Here you can see the results. The patch successfully created a clear image of a 3D printed letter G and even produced a B-mode image of a phantom designed to mimic a cyst in human tissue. This proves the device has real potential for detailed medical imaging. So let's recap the important points. This new technique allows for the creation of flexible ultrasound transducers. They're incredibly low cost at under $5 a unit. Their performance is excellent, with a high signal strength thanks to the porous graphene design. And they are capable of producing high-quality, two-dimensional ultrasound images. This technology could lead to a future of wearable health monitors that provide real-time diagnostics for things like cardiovascular health or muscle activity. It represents a major step toward making advanced, cost-effective diagnostic imaging more accessible for everyone. Thanks for watching Summarize Science.